A cylindrical capacitor, inner radius So a cylindrical capacitor with inner radius 0.1 millimeters and outer radius 0.8 millimeters has a rubber material between the plates. Its length is 3.2 centimeters. I'm trying to give here some numbers that is realistic. So if you go buy a capacitor Radio Shack, it might be this kind of a capacitor. It might have an inner radius of 0.1 millimeters, 0.8 millimeters, you know, and it might have some kind of rubber material in there. It might have a length of about 3.2. So it's a realistic capacitor. Okay. Now, say on top of this, the capacitor is hooked up to a 9-volt battery. Now we can answer a bunch of questions on this. We can say, what is the capacitance of the capacitor? What is its capacitance? We can say, what is the energy stored in the capacitor? We can say, what is the, I think pretty much that's it. Once you've answered its capacitance and its energy, because in order to answer its energy, you would also have to do we could ask this, what is the Q, the Q on either plate? If we can solve part C before doing part B. Okay, so in order to answer part A, we're simply now have to rederive the formula. We already derived the formula for the capacitance of a parallel plate. This one is a cylindrical plate, right? So what's the formula? Was it 2I or 102K, right? Was it like that? Oh, and then there was L, right? L. Is that it? I'm using the K version because it's here number to remember, 9 times 10 to the 9th. So we could say L is 3.2 times 10 minus 3. N of R2 is equal to 0.8 meters, 0.1 millimeter. So, and just put all that in, and then that's it. Oh, yeah, you're right, centimeter net 10 to the negative 2. Okay, so what's that going to equal? It's probably going to be pretty small. Oh, you know what? I forgot something. Now, since this one has a rubber material, right, we're going to have to multiply this by a factor of kappa. So let's see, did I write rubber there? 6.7, right? So the kappa of 6.7. So multiply this by kappa. Its capacitance is larger by that much. Now, the meter, you don't have to change this case because it's the same unit. So it'll just be ln of 8. Oh, that's small, huh? So 5.73 picofarads. So it's a capacitor that is about this big, and with those given dimensions and with rubber in it, it's still pretty small capacitor, picofarads. Okay, now what is the energy stored in the capacitor? Now, which formula should I use? Let's want to do B before I do C. So let's say I don't know Q. Well, I know that it's hooked up to 9-volt battery, so let me use the what? Q squared over 2C, half CV squared, half QV. So the one that doesn't have the Q is half CV squared, right? So then use that. That's pico, right? So half CV squared. And now we're going to get something like, it's going to be 40 times that, so it might get us in the nano range. Point 232 nanojoules. Yeah, it's going to give us in the nano range. So this one is joules because it's energy. And then now if I want to find the charge on either plate, so now I could say, well, I could either use the energy that we just got, or I can say C is Q over V, right? So if I want to find the charge, you do C times V. So this is pico again. So it's going to be 27 to 63, 65, 6, 45, 51 picocoulombs. So 51.57 picocoulombs, right? So that's a charge. Good. So that much is for today. Next time we'll pick up from here.